In mathematical finance, a Monte Carlo option model uses Monte Carlo methods to calculate the value of an option with multiple sources of uncertainty or with complicated features. The first application to option pricing was by Phelim Boyle in 1977. In 1996, Brody and P. Glasserman showed how to price Asian options by Monte Carlo. In 2001, F. A. Longstaff and E. S. Schwartz developed a practical Monte Carlo method for pricing American-style options. Methodology. In terms of theory, Monte Carlo valuation relies on risk-neutral valuation. Here the price of the option is its discounted expected value. See risk neutrality in rational pricing. The technique applied then, is to generate a large number of possible price paths for the underlying via simulation, and to then calculate the associated exercise value of the option for each path. These payoffs are then averaged and discounted to today. This result is the value of the option. This approach, although relatively straightforward, allows for increasing complexity. An option on equity may be modeled with one source of uncertainty, the price of the underlying stock in question. So, where is found via a random sampling from a normal distribution, see further under Black-Scholes. Since the underlying random process is the same for enough price paths, the value of a European option here should be the same as under Black-Scholes. More generally though, simulation is employed for path-dependent exotic derivatives, such as Asian options. In other cases, the source of uncertainty may be at a remove. For example, for bond options the underlying is a bond, but the source of uncertainty is the annualized interest rate. Here, for each randomly generated yield curve we observe a different resultant bond price on the option's exercise date. This bond price is then the input for the determination of the option's payoff. The same approach is used in valuing swaptions, where the value of the underlying swap is also a function of the evolving interest rate. For the models used to simulate the interest rate, see further under short rate model. Note also that, to create realistic interest rate simulations, multi-factor short rate models are sometimes employed. Monte Carlo methods allow for a compounding in the uncertainty. For example, where the underlying is denominated in a foreign currency, an additional source of uncertainty will be the exchange rate. The underlying price and the exchange rate must be separately simulated and then combined to determine the value of the underlying in the local currency. In all such models, correlation between the underlying sources of risk is also incorporated. See Cholesky decomposition #Monte Carlo simulation. Further complications, such as the impact of commodity prices or inflation on the underlying, can also be introduced. Since simulation can accommodate complex problems of this sort, it is often used in analyzing real options where management's decision at any point is a function of multiple underlying variables. Simulation can similarly be used to value options where the payoff depends on the value of multiple underlying assets, such as a basket option or rainbow option. Here, correlation between asset returns is likewise incorporated. As required, Monte Carlo simulation can be used with any type of probability distribution, including changing distributions. The modeler is not limited to normal or log-normal returns. See for example Data Matthews method for real option valuation. Additionally, the stochastic process of the underlying may be specified so as to exhibit jumps or mean reversion or both. This feature makes simulation the primary valuation method applicable to energy derivatives. Further, some models even allow for varying statistical parameters of the sources of uncertainty. For example, in models incorporating stochastic volatility, the volatility of the underlying changes with time. See Heston model. Least square Monte Carlo. Least square Monte Carlo is used in valuing American options. The technique works in a two-step procedure. First, a backward induction process is performed in which a value is recursively assigned to every state at every time step. The value is defined as the least squares regression against market price of the option value at that state and time. Option value for this regression is defined as the value of exercise possibilities plus the value of the time step value which that exercise would result in. Secondly, when all states are valued for every time step, the value of the option is calculated by moving through the time steps and states by making an optimal decision on option exercise at every step on the hand of a price path and the value of the state that would result in. This second step can be done with multiple price paths to add a stochastic effect to the procedure. Application. As can be seen, Monte Carlo methods are particularly useful in the valuation of options with multiple sources of uncertainty or with complicated features, which would make them difficult to value through a straightforward Black-Scholes style or lattice-based computation. The technique is thus widely used in valuing path-dependent structures like look-back and Asian options and in real options analysis. Additionally, as above, the modeler is not limited as to the probability distribution assumed. Conversely, however, if an analytical technique for valuing the option exists, or even a numeric technique, such as a pricing tree, Monte Carlo methods will usually be too slow to be competitive. They're, in a sense, a method of last resort. See further under Monte Carlo methods in finance. With faster computing capability, this computational constraint is less of a concern.